We have Professor Mahan Mj today from TIFR, who's a topologist and a geometer, and who's going to be talking about nature, shapes, and mathematics.
Okay. Yeah. Yeah, great. Thanks. This is sort of a first for me in this kind of a setup. Because more accustomed to talking to more specialized audiences. So anyway, let's see. So just in this run-up that was there, said a couple of things. So for instance, people looking at leaves and so there are two features which could possibly strike an individual, namely the shape of the leaf and the question about what is inside. And really, what we are going to be talking about today is essentially shapes in the abstract and an attempt at trying to understand what is inside, not in the loose three-dimensional sense, but if you look at all collections of surfaces, then what is it that is inside our common human understanding of them? So these are the two questions that we are going to pose and hopefully address it. So what are surfaces? So anything you see is a surface. So essentially, a fairly large, grandiose way of saying what our surfaces is all visual information. Yeah? Why? Because when you see something, by the dint of the fact that we as human beings are three-dimensional creatures, when we see anything, we usually see only the surface of that object. Yeah? So surfaces are all around. Yeah? I mean, the surface of this laptop, the fan, the wall, the curtains, all these are. So if you forget for the time being that you're imagining these to be something solid where there's something inside, then your view really, literally, is stuck on the surface. Yeah? So that's all visual information that we are trying to understand. And let's take a sampler of what's the, I mean, so this it's a huge amount of information. So we would like to understand it, categorize it. And here's a sampler from, not from this room. So the first slightly interesting shape we come across is the surface of a globe, and then there's a whole range of them. So there's stuff which is more exotic, I mean, who knows what this is, and so on. Yeah? So let's just do this a few times, and then we'll start with trying to understand the problem. Yeah. So you can buy this by just looking around you and just looking at these few slides I've randomly collected here. You can understand that if we are to try to understand this entire amount of visual information, it's a pretty formidable task, right? So how are we going to, so basically, I mean, when we want to say that we want to understand it, I mean, this is a sort of a common trait. We would like to comprehend what we are seeing, and therefore, we need a framework within which to organize all this visual information. And at the end of the day, we should have a way of saying that, look, this is exactly what we mean by understanding all this information. So what's the framework that we are, I mean, you need a framework within which to organize this information. Okay? So what exactly, so basically before, yeah, we'll say that we would like to understand, but it's important to know what we mean when we say we would like to understand all this information. So it's not that any answer to that question, what we mean by trying to understand, there's no real definitive answer. We'll propose one framework here, and even within mathematics, there's a whole range of frameworks. And probably towards the end, I'll give you another framework which is related to the first. But there's a whole slew of them even within mathematics, so I'm sure there's stuff outside also. So first, let's try to understand what we mean by trying to understand all surfaces. And so what we mean is essentially because we need a method of abstracting out this information, yeah, putting it on paper and communicating to others. And we need a formal structure We need a formal structure, formal mathematical structure within which to put all this stuff. So I mean, somehow or the other, so let's see, let's start with something, and this will illustrate my point. What is the shape of the Earth? Anybody? Huh? Somebody else? Yeah, somebody, I heard some.
Spherical?
Yes, go ahead.
It's like a sphere, but
It's
it's
like
slightly
a-
flattened at the poles.
All right, it's like a sphere slightly flattened at the poles. All right, very good, excellent. And there was somebody who said it's a geoid, etc., etc. All right, so let's, yeah, so the first shape that we had shown here was that of a sphere, yeah? But this explanation of the shape of a sphere, of the shape of the Earth as something that is slightly flattened at the poles, you have already performed a certain simplification of the shape of the Earth. For example, this room and this ladder here, that's also part of the shape of the Earth, correct? But that somehow, it's something that we have forgotten. So we have abstracted out some essential feature, some essential large-scale feature, which captures the shape of the Earth. So this is disregarded there. Yeah? So a lot of finer features are disregarded, and this is the way abstractions proceed, right? So if at the end of the day so where does the sphere live? I mean, yes?
Could we just pause for a minute and just organize?
Absolutely, go ahead, no problem. All right, so so we were trying to, we were trying to understand the statement that the shape of the Earth is spherical, and in making that statement, we have really abstracted out some information. Yeah, we've forgotten what we think is inessential and retained only certain essential features, and that's the process that we do. See, the point is there's a huge amount of information constantly bombarding our system, and unless we perform this operation of filtering out, also called focusing, also called attention, we are not going to be able to understand essential features. Yeah, it's a process. I mean, it's something that we always do, that we constantly do. Our biological systems are shaped that way. Yeah? I mean, so for example, when we start focusing, some things become highlighted, some things fall off. So saying that the Earth, the shape of the Earth is spherical, is actually an attempt at doing this. Yeah. So you're already beginning to understand intuitively, how the human system processes shapes, processes visual information. So we'll take that particular feature of our system and proceed a little further and get at the kind of formal structure that we are going to be using. Yeah. So we need to understand. I mean, so I said all visual information. That's too anthropomorphic notion. We need to get it to a place where the structure is more formal, and so we need a formal notion of what surfaces are. And much of this, I mean, the first maybe quarter or one-third of this lecture is really understanding what the problem is. Yeah. So vaguely, it's something like starting off. Oh yeah, we'd like to understand all visual information. Great, fantastic. I mean, if you stay stuck with that, nothing will ever progress. So we'll have to move towards an understanding of what we mean by that problem. Yeah. So surfaces. So let's start with a slightly more formal notion than all visual information. And essentially, so we capture just this one feature, which this loose discussion that has gone on till now, that instructs us. Essentially, when we see something, our view is stuck only on the surface of this. So which means when I am seeing this book, I am not seeing it really as a three-dimensional object. I am seeing only the surface of the solid object. By a certain habit from childhood, we deduce that it's the surface of a three-dimensional object. But, I mean, why stop at 3, right? Okay, just because we as human beings are three-dimensional creatures, we are equipped, we are, I mean, almost accustomed to thinking of space as 3 dimensions. So there is no real reason there. So let's see that. So when we are talking about surfaces, we are really talking about surfaces of solid objects, which means if we zoom in and assume that you're a small little ant moving on the surface of a book, then what is the world around the ant? Yeah? So try imagining the shape of what you are seeing seeing around you from the perspective of the ant. Yeah? So it's some local 2-dimensional flat space that one is looking at, right? So that's the world according to the ant. And I mean, in spite of considering ourselves as a much more intelligent species, a few hundred years back we thought that the Earth was also like that, right? So essentially it's only when there's a view from far, yeah, not this myopic view, that you realize that it's actually a spherical thing sitting inside 3-dimensional space. But locally it all looks flat. Yeah? So yeah, I mean, even our worldview a few hundred years back, maybe 1,000, maybe a little more, was that it locally looked flat. Yeah? So basically the surface of the Earth is an example of what we are calling surfaces here, locally 2-dimensional objects. All right? Now let's come to, so what are we doing? We are going to proceed in a twofold way. First, the objects we are trying to understand. We started off with all visual information. Now we've made it more specific, called them locally 2-dimensional objects. That's one thing. So in the first sentence, we would like to understand surfaces. Yeah. So there are 2 crucial words there. One is surfaces, one is understand. Yeah? And we'd like to understand both these words properly. Yeah. So we've understood what surfaces mean, but we would like to understand what understanding means. Yeah. Right. So let's try to put this. So comprehending them means classifying them in some reasonable sense, but we need to have a framework for classification. So what does that mean? So we want the following. So yeah, surfaces, locally 2-dimensional objects, classification, what it means, the formal structure is here. First, we want an exhaustive list. Yeah? You can't say, for example, I mean, suppose somebody says, okay, there's the surface of this curtain, there's the surface of this lampshade, the surface of a fan, the surface of a sphere, etc., the surface of a small sphere, big sphere, geosphere, flattened sphere, etc., and there's this whole slew of things. So you want to put all of that in convenient, neat dockets. Yeah? So we want a whole collection of dockets such that what happens, any piece of information that you're interested in classifying fits into one of those dockets. Not only does it fit into one of those dockets, it fits into exactly one of those dockets. Yeah? So first says that it fits into, if anything you see fits into one of these dockets, it just means that there's an exhaustive list and no 2 dockets overlap. Yeah? That's what this means. Yeah? An exhaustive list of, think of these as dockets. Yeah? So for example, books less than 100 pages, books between 100 pages and 200 pages, 200 pages and 300 pages, 300 pages and 400 pages, and you go on listing them out, right? So at gaps of 100 pages, right? So presumably the collection of books, once you cross 10 million, that set will be empty, but who cares? Yeah. So, but there's still, I mean, it's an infinite list, possibly, but any book that one can come up with is going to fit exactly one of those dockets, right? So that's what this means. So a list with no redundant elements. That's one thing that we need in this framework for understanding surfaces. Second, given something that qualifies as a surface, which means it satisfies this definition of being a locally two-dimensional object, we want to say precisely which object in this list it is. Yeah? So we need a method for determining. So if it's a collection of books, you pick up the book, hopefully nobody has tampered with it, you look at the last page, you see the page number, and you fit it neatly into the docket window. So if it's got 378 pages, it fits into the 301 to 400 docket. Okay? So there's a method. Yeah? So there's a method. You pick up an arbitrary object, look at some feature of it, determine which exact docket in this collection it fits into. Yeah? So what I told you just now, pick up the book, look at the last page, observe the page number, and then check which 100 block it belongs to. It's a finite number of steps, and at the end of finite number of steps, you have determined an exact docket. Yeah? Which means you've solved the problem of which block in this collection it belongs to. This method, this process is going to stop in some finite number of stages independent of the book you start off with, right? This is what's called an algorithm, okay? A method of determining an answer, yeah, which necessarily terminates in finite number of steps. That finite might be pretty large, but who cares, yeah? So this is what we are really trying to get at. So given a locally two-dimensional object, we want to say which object in the list it is, which means which docket it belongs to. All right. Second, this is equivalent. Basically, suppose you have, what does it mean? You've said that this guy fits into this docket. Somebody said that the Earth's shape is spherical, yeah? Or flattened sphere, etc., etc. Now, if I take two flattened spheres or two spheres, yeah, and tell you, okay, so are these the same thing? And yeah, these are both spherical, which means you've forgotten some extra information and you have said that both of these are really the same. And what you have left unsaid is that you are forgetting some inessential part of the information, and then you are going to be able to say that they are the same. So saying that a particular new object belongs to one of these dockets is effectively the same thing. Yeah? Anything? No? Is effectively the same as saying that you pick up two objects and then in a finite number of steps you will be able to say whether they are the same object or whether they are different. Yeah? Okay, fine. So we were trying to understand what comprehension means, and therefore we said that, okay, so you have an algorithm, a method of determining, you pick up an arbitrary surface, you say in finite number of steps which docket it belongs to, which is the same thing as saying that you pick up two arbitrary objects, you determine in some finite amount of time by finite number of steps whether they are the same or different. Yeah? So in this particular shape, when somebody is saying that the shape of the Earth is spherical, and somebody shows him the picture of an Earth, somebody shows him a globe here, one would be tempted to say they are the same. Correct? But certainly the globe and the Earth is not the same. Yeah? In a certain other context, they are not the same. So we are really, what we are leaving unsaid is that there's a lot of information that we are forgetting, and which we are in a particular universe of discourse, particular context, we are defining, we are limiting ourselves to this is the essential piece of information that we are going to be looking at, and the rest can be forgotten. Yeah? All right. So that's the problem. So now what is the list? So let's go on with, now we are going to make both these methods. So first, what is a surface and what does comprehension mean? We are going to make these more precise as we go on. So let's look at again. So the first set of surfaces we looked at were fairly concrete things which we saw around us. Yeah? We are going to be more specific where we are going to look at pictures of more abstract objects. This is certainly not the not a picture of the earth. I mean, there's no water, there are no countries, etc., etc. But essentially what the study of topology does is that politics is completely irrelevant. So the countries it's divided into, it's irrelevant information. It's been taken and put in the garbage can. Okay, and what you have left is this. Yeah, and this is really what's going to be important for us as mathematicians or as scientists. So this is one, and now you have a shape of a rabbit. I mean, these are you typically designed using computers. So you can see that this is, I mean, these little things, these are like pixels, and it's basically taking an abstract shape of a rabbit, and then you're putting it down. And if you look at, say, a small part of the rabbit, say here, take a small little square there, and you see at the corner, that looks locally like a little piece of graph paper where the sides are tilted, correct? You go back to the picture of the sphere, and you look at one of these little rectangles around here, you take it out, and then it also has, there's an x coordinate, there's a y coordinate, correct? So this also, locally, it looks like graph paper. Locally, the rabbit also looks like graph paper, correct? So what does it mean? Now we try to make this notion of two-dimensionality more precise. What does it mean? Locally, if you look at a small little patch around wherever you are situated, so assume you are situated at a point, you look at a small little patch around yourself, and then you have these two coordinates, and so if you want to proceed here from any one point to any other point, think that these are the y directions and these guys are the x directions. And if I tell you that you proceed some m number of steps in the x direction and n number of steps in the y direction, I'll be specifying exactly where you are. So assume for the time being that Mumbai was an extremely well-planned city where all the roads ran from east to west or north to south. And starting at any point, I can specify for you the exact coordinate. So then the model of such a model city would be what locally the rabbit looks like. So this is another example. Think of a city which is very well planned, and you're looking at the surface of the earth locally, which means essentially in the city around you. So that's an example. So these are all examples of two-dimensional surfaces, which means every point has a small little neighborhood where you can put x and y coordinates and everything is determined precisely. Okay, so now let me get to formal definitions. It's just a way of nailing down what we have said so far. But so mathematicians, I mean, a certain occupational hazard of being a mathematician is unless you nail it down exactly and precisely, and so that it's not going to confuse, we don't really mind if somebody does not understand it. But if somebody does, then that person should not have a second interpretation. So we want to have a common interpretation so that ideally if somebody learns that language, then one will have an exactly correct, so this is sort of a mental ideal of precision that we have, and this has been going on since Plato, since before that. So, and we are quite happy with that. And if somebody tells us tomorrow, well, the earth is not spherical, the real world does not fit, so much the worse for the real world. Okay, so now let's put this formal definition down. A surface, and this is what I was trying to get at when I was saying that, okay, so the fact that we as human beings are three-dimensional creatures is not, in a more democratic setup, we don't occupy some special place of privilege. So the fact that we are three-dimensional and we see two-dimensional features, there should be within ourselves a system which manages to abstract things out from there. So this locally two-dimensional, which is the notion of a surface, that number 2 is separated out, and so you call a surface a fairly humble object. It's a two-dimensional manifold, shortened to two manifold. Manifold means just something that locally looks like Euclidean space. If you needed 3 coordinates, you would call it a 3-manifold. If you locally had 50,000 coordinates, it will be a 50,000 dimensional manifold. Okay, so this is not. I mean, it's not entirely whimsical. Spaces which are locally 6-dimensional are occurring more and more in theoretical physics. In many computer science problems, larger number of dimensions starts playing a role. Anyway, so what we are doing is really doing the simplest classification problem, which means locally 2-dimensional objects. They've got a name. These are 2 manifolds. And this business of being able to put locally x coordinates and y coordinates is what it says. The technical mathematical term is being homeomorphic to. It basically says this R2 is essentially what you would call graph paper. Yeah? So what we've stated informally, now we are stating the same thing formally. Okay, so we've seen closed shapes, several of them so far, which are locally 2-dimensional, which are examples of surfaces, examples of objects which we are trying to study. Are there any others? Young friends here.
Like, what do you mean, like, any locally 2-dimensional object?
Yes, and just see around here. I mean, this is something which with a very different shape.
For example, the library shelf, it's divided into squares and rectangles.
But what would be the shape? I mean, this is where it would get stuck, right? So you would be seeing something. So assume this was made of some piece of paper which you could, if you could blow from behind, then it would all just become flat. Yeah. So that would still be the shape of a sphere. So is there something else? Something essentially different? Yeah?
The coffee cup.
Ah, fantastic. So this is, so this one. So the surface of this cup, yeah, this is something that's different. And here is a deformed coffee cup. Okay? So you look at this coffee cup, assume it's made of plasticine, yeah? So flatten out this part, it's going to become a round ball, and it's going to have a loop here. And you look at the surface, it's going to look like that, yeah? So essentially the surface of a bicycle tube, surface of a donut, surface of a coffee cup. This is, and again, these are very anthropomorphic names, so we remove that and call it very unromantically a torus, okay? So, okay, so that's what we do. We take a sphere, now we have a torus, and just as surfaces, I mean, all that anthropomorphism was thrown out. We call them 2 manifolds, 3 manifolds, n manifolds, and by some historical accident, 2 manifolds are also called surfaces. So this is an example of a torus. All right, and now the other part of the problem. So we've gotten examples. Now the other part of the problem, meaning to classify them, when we have to say when 2 objects are the same. And so 2 surfaces, same means, the word same means different things in different contexts, right? So it does not, same is not same everywhere, right? So therefore we need to define what same means, and it's therefore best to again throw away the word same and use a more technical term, which will involve precisely our universe of discourse. Yeah? So our context. So yeah, again, I keep lapsing into mathematical terminology. So universe of discourse is exactly what we otherwise, as normal human beings would call context. Okay. So 2 surfaces are same in the world of topology. We don't use the word same, we call them homeomorphic. If you can pass from one to the other by setting up a bijective correspondence. So every point in the first space goes to exactly 1 point in the second, and every point in the target comes back to exactly 1 point in the first. So this is just a setting up correspondence between points, but more than that, this is a method which does not tear nor glue. Yeah? So tearing is a discontinuous operation. Formally, these are called continuous maps. So you have a continuous map, which is a bijection. Bijection means this 1-to-1 correspondence. Every point corresponds to a unique point. And you have an inverse map which is also continuous. So if you go from one to the other continuously, you can also come back from the second to the first continuously. It's not a priori true. Yeah? If you can go from the first to the second continuously, you cannot necessarily come back from the second to the first continuously. For example, here's a process. Take a string. Yeah? This is a one-dimensional object, locally one-dimensional object. Take the two ends, bring them close together and paste them. Yeah? This is a continuous motion, right? You're bringing something together and pasting it. Yeah? If you have to go back, you'll have to tear. Yeah? So something that was continuous suddenly becomes two pieces locally. That's a discontinuous operation. So from the first to the second, from the interval to the circle, you can go continuously. You cannot come back continuously. Yeah? Yes?
But then aren't you, if you're doing the two ends,
Yeah.
earlier what was discontinuous, now you're making it
Yeah, that's right.
continuous.
That's right.
So that's allowed.
Yes? No. So what does it mean? It means basically you take your string in two-dimensional space.
Yeah.
You move it. Yeah? And then at some point, this motion is a continuous motion. It comes and sticks. Right? Now assume that you are, that's, so basically take any point on the end. Yeah? It's moving continuously. Right? So then what is happening is that two points are coming and merging into one point. Right? That's the forward direction. When going back, that merged point is now regarded as one point. So two points are, what does continuous mean? You look at any point on the space and you look at its trajectory under this motion. That has to be a continuous motion. Okay? All right? Things which are close by will move to close by points. Now, when you want to cut that, you have to send it either to the left or to the right. And you don't know which direction. So democratically, it would go to both the left and the right. Yeah? So, and that would, so that's not a continuous operation going the other way. Yeah? Okay, but all this, I'm conveniently putting all the technical stuff under metaphorical carpet. Yeah. So anyway, so this is what we mean by the same. I'll give a more intuitive understanding of this notion now, right away. Intuitive idea is that you can go from the first shape to the second shape by a continuous process of deformation. Yeah? This is what homeomorphism means. What's an example? So you have this ineffective dumbbell with 3 bells, yeah? And you start deforming it. Yeah? So essentially what's happening is that the parts which were more bulging, those are becoming narrower and narrower, yeah? Less curvature. And the sharp, narrow necks which were in between, those are swelling up, right? And in the process, once you've gone here, the narrow necks have all but vanished, and then essentially it all becomes nice and round like a sphere, yeah? So essentially, that dumbbell with 3 bells and this round sphere at the bottom, they are the same object in this context of topology when we say that two objects are the same if they are homeomorphic. Yeah? Which means the first can be deformed continuously to the last, and you retrace these steps, and you're going to go from that nice round sphere at the bottom, which is almost a nice round sphere. It's a flattened sphere, flattened slightly at the top and the bottom. If you flow it back, you're going to get this, right? Yeah. So here is another example. You have a crinkled lemon here on the left, and you start flowing it in the same way. It becomes smoother and smoother, and then you have a nice round sphere at the end. Yeah? Okay, so that's what it means to for two guys to be the same. So we've now understood at this point what shapes are and what we are trying to mean when we say that we are trying to understand them. Yeah? So the problem has been posed reasonably precisely now. Now we do the classification problem. Basically, we'll address the original problem, classify all surfaces. Yeah? So now this is an exercise I'll give you now. Yeah? Okay. So now let's look at 3 pictures, and you are going to solve this problem. Yeah? Yes? You have a question? Go ahead. Feel free to interrupt and ask. Okay. So now look at these 3 shapes. Yeah? There's something like a teapot with 3 handles, which you can't drink tea out of. And oops. And you have this one. It's a chain of 3 loops. And you have 3 loops arranged all around the central thing. And you assume that it's only the surface of these solid objects that we are looking at. Yeah? So these 3 shapes. Now, question, are they the same, are they different?
Same.
You say they're the same? Yeah. Anybody votes for different?
1 and 2 are same.
1 and 2 are the same. Very good. What about the third? Third is not the same?
I have a question.
Yeah.
Although they all have 3 holes, they all have 3 holes, but how can we say that they are the same? Because their curvatures at different points will be different.
What is the meaning of same and different? I have told you specifically what the meaning of same is. You can deform one to the other continuously. If they can be deformed one to the other continuously, they are the same. If they cannot be deformed one to the other continuously, they are not the same. Same means this in this particular context. It will mean a different thing in a different context. Yeah? Yes? Young friend here?
The first shape 1 and shape 2 are the same, while shape 3 is different because its mass has changed. So you can't change it back to one.
No?
The first or the second.
No? The mass is it's a two-dimensional thing. Mass is completely irrelevant here. We've thrown out mass and all that stuff as completely irrelevant information. Yes, just the surface. So assume if you want to have a model, think that these are made of very flexible rubber sheets, yeah, which has been bent and glued in these shapes. Can you go from one to the other? Yes? But you had voted that all 3 are the same, correct? Or no? No? Somebody. You are still thinking? But you'll have to answer this one. I will not answer it for you. All 3 are the same. Why?
If you look at them from
Okay, let's look at it one by one. All 3 are the same is what you're saying. Okay, so let's look at first and second. So this one and the second one. Why are these 2 the same?
we will have to just move the center part a bit.
Yeah. So assume that this is all made of very flexible stuff. You're catching hold of this handle and then you're sliding it. So it's becoming, it's moving towards the bottom. You slide it further, distorting this fabric along with it, but it's got infinite elasticity, so you can distort it. Once this is moved to the center, and what has happened is that you've gotten back this first one, right? Okay, so this is really, this is the kind of hand waving that is allowed. So basically you can see demonstrably that, so essentially if you take this handle and you stretch it and move it to the bottom, on this side you'll have this straight shape, and so the first and the second are the same. All right, that's very good. What about the third one? What about this one? The third one and the first 2? Yeah?
You can just deflate that center balloon like
Exactly. So assume that this is made of some flexible material like plastic or rubber, and then what you do, assume that this is made of this is a balloon which has been inflated, so you let out some air, it becomes flat, and then what do you get? You essentially get the first picture back. Yeah? So essentially this part in the middle is that balloon deflated. Yeah? So you're letting out the inessential, you're removing more and more inessential information, and you're getting back this. So all these 3 guys are the same. Excellent. So here is the classification theorem. So in our context, any closed orientable surface. So surface we've already said, yeah? What does closed mean? It means that it has no boundaries, you don't fall off the thing, and it's trapped in a bounded amount of space. Yeah? That's what closed means. All these surfaces were closed. Yeah? So if you had, for example, an ant traveling entirely on the surface of this, there's no edge. It would go inside, then come out, and then come back here, and then it would keep going round and round. Yeah, that's what closed means. On the other hand, if you just had say this 2-dimensional top of the book, and it started going off here, and then the edge, assume that it's infinitely thin, then you go to the edge, you're going to fall off, right? So this, just the surface of a disk, it has an edge, namely the boundary circle of the disk, yeah? So that's not closed, whereas if it closes in on itself, it's called closed, that's it, yeah? So that's what a closed surface is. The second word, orientable, for the time being, assume that any surface which sits inside three-dimensional space and is closed, yeah? So if you have a closed orientable means a closed surface which can exist in our three-dimensional world. Okay? For the time being, let's assume that. We'll come to what that word means more specifically a little later. Then that is classified by an integer, positive or 0. This is exactly, any such closed orientable surface is a sphere with some n handles attached. So we go back to that picture. This is a sphere with 3 handles. You could have 2 handles. If you had just 1 handle, you'd have the coffee cup or the torus. If you had no handles, you'd have the sphere, and that's it. So there's a theorem. This can be, so basically here's our classification theorem. What was it? The example that I was giving is you pick up the book, look at the last page, see the number of pages, see which 100 it fits into. Here, what are you going to do? You pick up the surface that you're looking at, assuming it's closed, look at the number of handles, it's 1, therefore it's a torus. Okay? So that's the algorithm in practice, yeah? Some finite number of steps. Theorem tells you that this is an exhaustive list of dockets. You just count some number of handles and you've classified it. Okay? And therefore, so basically from this point of view, this cup, the surface of this cup, the surface of a donut, the surface of a huge cyclotron machine which crosses several continents, a bicycle tube, all of them are the same surface. Yeah? The geometry of the surface curvature is completely irrelevant here. Okay, good. So this is our theorem, but it had one particular term there, which I used, which is this word orientable. What does it mean? Yes? Closed surfaces. Yeah, closed surfaces are necessarily compact, but not all compact surfaces are. Local two-dimensionality is, closeness means, yeah, closed implies compactness. Yes, we are talking about compact two-dimensional manifolds without boundary. You're not supposed to be a mathematician. If you are a mathematician, you're not supposed to be here. Okay. So let's see. So what does orientability mean? Yeah, orientability is also a local feature. I mean, it's not something that. Orientability is a global feature. It's not a local feature. And I said something about if it's a closed surface, then what it basically means is that it has well-defined sides. What are sides? Let's go to a picture and illustrate. Has anybody seen this painting before? Yes? It's not painted by Wikipedia, yeah? It's painted by a painter. Who is the painter? Escher. Yeah, that's right. So it's painted by Escher. Good. So, and there is, like many of Escher's paintings, this has a mathematical point to it. Yeah? He has drawn these ants crawling around so this shape, I don't want people who know the name to tell me the name. I would rather like people who don't know the name to think of how you would go about constructing this object and what is special about this object. So what's happening here? So we said that a surface is orientable if it has well-defined sides. Yeah? So why do you think Escher has drawn the ants here? So think of these middle legs. Yeah? So what is a side? If you try to think of it formally, you have a two-dimensional surface. A side means a perpendicular direction pointing out of it. It can point either in the upward direction or in the downward direction. Correct? Choice of one of those two things is a choice of a side. Okay? So if you look at the middle leg of this ant, it's pointing upward from here. Yeah? So that's a side. Now follow the ant around. It goes here, and this is why he has drawn these ants. Essentially, he's following the ant around this gadget has a name, it's called a Mobius strip. Anyway, when you follow it around, you come to this ant. And then this ant would go right below this, and this middle leg would point right in the opposite direction. You can see that? That's the point of drawing these ants. That's the mathematical point that Escher is trying to illustrate here. Which means that you take your normal. Now let's throw away all the art from here and get back to just the underlying mathematics. Think of this two-dimensional strip as a mathematical object. Think of the normal, forget the ants. Follow that normal around. When you come back here, you're going to get the normal pointing in the exact opposite direction. Yeah? Which means what? This Mobius strip does not have well-defined sides. It's not closed. Why? So assuming that this gadget is infinitely thin, it's made of, so you can do this. So how do you build this Mobius strip? Take a piece of paper, take a notebook, cut out a thin strip of paper, flip one side by exactly 180 degrees, paste them. If you do that without flipping, you're going to get an annulus, yeah? Cylinder, yeah? Yeah, again, a cylinder is in mathematical terminology called an annulus. But if you flip it and paste it, you're going to get this Mobius band, yeah? And that does not have well-defined sides. On the other hand, it has edges. This part is an edge, which means what? Which means assume that this ant was much smaller, and this is all that it would, this is the entire world that it lived in. Once it reached this edge, it would fall off, yeah? Much like the flat earth fanatics from long ago, who thought that if you go sufficiently far on the surface of the earth, you're not going to come back where you started from, you're going to fall off, yeah? So something that is not closed is intuitively something that you fall off, yeah? But if it's a surface on which you go round and round, that's something that's closed, okay? So this is not an example of a closed orientable two-dimensional manifold, not a closed orientable surface, yeah? It's not a closed surface at all, yeah? So it doesn't come under that list that we've talked about already. And there's a very good reason that we don't talk about orientability, except when we talk of closed things inside three-dimensional space. They cannot exist in three-dimensional space. That's a fairly simple theorem, but fairly simple once you know the technology. Yeah? Do you know this? Yes? Very good. All right. Where do you... IIT Mumbai in? Maths? Oh, I see. Okay. So you had a course on algebraic topology? Oh, okay. Very good. So what is the theorem? I'm sorry. No. I'm asking for this simple thing, that if you have a closed orientable surface, so there is something essential here. So it's a general fact. You take a closed n-1 dimensional manifold which can be embedded in Rn. 2 is a special case, okay? So n-1 equal to 2 is a special case. You cannot have that. Any manifold which can be embedded in one extra dimension necessarily has two sides. This is a serious fact. It's not a trivial fact. Yeah? It's an algebraic topology fact. It's not a trivial fact. Okay. Trivial and non-trivial, it depends on once you've read it and it's true and you know the proof is of course trivial. So anyway, so let's get on with trying to understand what closed surfaces are. And this is what you're doing here. See, the construction of the Mobius band is you took this narrow strip, flipped and glued. Yeah. What if you do it with a cylinder? Yeah? Long narrow cylinder, and you take the boundary circle and the initial circle and you flip and glue. If you don't flip, yeah, you're going to get a torus, right? Bicycle tube. But if you flip and glue, you're going to get this object. This has a name which I'll come to. But essentially note that it intersects itself in this round circle here. Yeah? There's a part where it intersects itself. But so that means locally there, it looks like a sheet cutting into itself. So locally, if you look around there, there's going to be one two-dimensional thing in one direction, there's going to be another two-dimensional thing in another direction. It does not look locally two-dimensional. Yeah? So intersections like these are not supposed to occur in a two-dimensional manifold in a surface, equivalently a surface. So which means what? In order to do this flipping and gluing and putting the picture inside 3 dimensions, we are forced to lose our manifold property. We are forced to lose our locally two-dimensional property. Means it's not a surface anymore. Now, so essentially this is the best approximant to a closed non-orientable surface that we can see. But assume that you can move up an extra dimension to remove this self-intersection. Yeah? That can be done, but it will have to be done in some 3 plus 1 equal to 4 dimensions. Maybe at the end, if somebody is interested, I can tell him or her about it. Okay, so let's see another picture of this. And this is an actual model. This is made somewhere. Basically, it's so this is an example of a Klein bottle where the stem has now been, but again, this is a part where the glass has been forced to intersect itself. Yeah. So essentially, when you try to put something that is closed and non-orientable inside 3-dimensional space, you are forced to intersect yourself. Okay. So now we have essentially understood what we mean by and why it's a fact that these closed non-orientable things do not arise in 3-dimensional space, because then you cannot have well-defined sides. And if you do have well-defined sides and if it's closed, then you have an exact number, 0, 1, 2, 3, 10 power 23, etc., etc. Something which determines that which equals the number of handles and determines exactly which surface in that collection it is. Yeah? But a sphere, and then so I was keeping on trying to induce you to forget this irrelevant information. Yeah? Which means there was this fiat saying that this information is irrelevant. But immediately there should have been this protest. Why is that irrelevant? Yeah? So now let's try to make it relevant. Yeah? So basically now what do? We forget a lot of information and do this first step of classification. Now pick out one of those objects and look at the information that we have forgotten and put back some of it. Yeah? So there's more. So now so this is what we have been talking about so far. This notion of equivalence has a name, and the field of study is called topology. Yeah? But now let's put back shape in a more precise sense. And he was mentioning this point about things being curved. So let's put back curvature into the picture and try to understand what these things are. So these shapes are different at a slightly subtler level. They can be deformed one to the other, but there is curvature. Yeah? And the field of study which captures curvature in addition to shape is what is called geometry. Okay? So a rabbit, the surface of a rabbit, it's a sphere. Topologically, it can be deformed to a sphere, but there are sharp shapes. For example, the tips of the ears are pointed, so they are not round and not nice and round like a sphere. So they are not geometrically a sphere, they're topologically spheres. And geometry, roughly think of it as curvature. And I'll illustrate by these. So these are solids which have been studied for, anybody guesses? These are examples of certain solids. Yes, please.
Are they regular solids?
Yes, they are regular solids. Who studied them?
I'm not sure.
But guess. Have a guess. No. If you know the answer, you are not supposed to. So I would like to invite guesses on how many years these things have been studied for. Anybody has any guess? 200, 300, 500, 20, 10, 5, 2, 1.
I would say around 500.
You would say around 500. Good guess. Anybody else? Anybody else has any other more courageous guesses? Yes?
2005, yes.
No, if you know the answer, you're not supposed to say. Why? Who studied them?
Plato.
Yeah, so these are called Platonic solids. Yeah, so Plato studied them. What is special about these solids? All the faces are the same. The same meaning, the faces are now polygons. Yeah, and they are polygons which are same in the sense of Euclidean geometry, which we study in class 6. Yeah, which we start studying in school. Two shapes are congruent if one can be moved to the other and without changing anything else. So they can be translated. Vertices go to vertices, edges go to edges. Everything just fits up. Yeah. So that's what we mean now. Same for two-dimensional geometry is in the sense of Euclidean geometry. Yeah. So all the faces of any object are the same. Each vertex has the same number of edges hitting it. Each face. Yeah, so these are called vertices, these are called edges, these are called faces. So each vertex, zero-dimensional object, has same number of edges. Each edge has, each face has same number of edges. Yeah? Okay? So that's what's called a Platonic solid. And this list here, this is called a dodecahedron. Yeah? It's got 12 faces. This is called a tetrahedron. It's got 4 faces. This is called an octahedron. Yeah, so these are all, dodeca means dec plus do, means 12, 10 plus 2. Tetrahedron is tetra is 4. Octahedron is 8. A cube has 6 faces, but we call it a cube. This is an icosahedron. It's got 20 faces. Okay? And that's it. It's a basic theorem of this kind of geometry, that this list of 5 is all that we have in terms of Platonic solids. This is a classification of Platonic solids. And again, the same stuff, but in a different material. And the material, whether it's wood or glass or diamond, is completely irrelevant to us. Okay. So now let's do, let's see a show of hands. So for example, which of these objects do you think is the point, the vertices? Which one has the sharpest point? So yeah, imagine, don't do this physically, but imagine if you take one of these objects made of the same material and you poke yourself with it, which will hurt most? Yeah? The tetrahedron. And which will hurt least? Yes. The one with the 20 sides. Fantastic. Now, why do you say that? Yes.
Because the less the size, the more the angles have to cover. So the angles become more sharp and more point, and so the vertices become more pointy, and therefore.
Very good. Okay. So now let's try to. So this is exactly how we start thinking. The first answer is blurred, unfocused, but it has some content. And then we try throwing the garbage out of that and get to a precise notion. Yeah. So what he is saying is that the angles at these vertices is less for the tetrahedron and more for the icosahedron. Yeah. What does it mean to say angles at that vertex? Are we talking about just this angle here? So for example, yes?
Every angle in perspective, like it can be in height, length, and width.
See, finally, you see, now we are going to try to be very specific, yes? So finally, you'll have to give me a number associated to every vertex, yeah? Again, we'll have to do this de-anthropomorphization process and associate to every vertex here a number which will tell us how curved it is. Yeah? And then we are going to be able to compare. Some number is larger, it's less curved or more curved, whatever. So basically, larger or smaller is going to determine more curved or less curved. Yeah? So we are going to map this whole thing to numbers. Yeah? How are we going to do it? So have a guess. So if you have, let's say that no curvature, yeah, is something we'll assign 0. Yeah? Okay? So this is a normalization. So what is something that will not hurt at all? Yes?
Piece of paper.
A piece of paper. Okay. No, so what, locally, we are looking at a vertex, yeah? Yes?
A vertex of a Googleplexian Googleplex.
It has 10 power 100 sides. Let me tell you that suppose we have something which has 10 power 23 sides, faces. 10 power 23 is certainly greater than 100, right? 100 is just 10 power 2.
No.
So
Google has 100 zeros.
that's right. So that's
Googleplex has
10.
Google zeros, and that exceeds the atoms in the universe. Googleplexian has Googleplex zeros, and Googleplexian has Googleplex zeros.
Right. So the number of number of electrons in the universe is something of the order of 10 power 90. Yeah, which means 1 followed by 90 zeros. Yeah. Do you know? I mean, so that's the most physically relevant number. Yeah. So let's take this aside to another discussion. So there is a certain number which has mathematical significance. Yeah. 10 power 10 power 10 power 32. See, the problem with all this terminology, Googleplex, etc., is that beyond a point you'll have to keep inventing new words. Yeah. Right? So we just write this 10 on top of that 10, which means if you had just 10 power 10, it will be 1 followed by 10 zeros. But 10 power 10 power 10, which means 10 power 10 is 1 followed by 10 zeros. 10 power that number is 10 power 10 power 10. Yeah? So 10 power 10 power 10 power 32. It's a tower of 4. Yeah? This is a much quicker way of increasing numbers than say going from Google to Googleplex, etc. Yeah? So 10 power 10 power 10 power 32, yeah, which is certainly orders of magnitude larger than the number of electrons in the universe, does have mathematical significance. Yeah? And it's related to a certain fundamental number theoretic problem. Do people know what prime numbers are? Yes? So you look at this, what are the number of primes less than a certain number n? Yeah? And there's a fundamental theorem which was proven around the turn of the end of 19th century, early 20th century, which essentially says that this approximately asymptotically goes like x by log x. Yeah? So if you take very large numbers, the number of primes less than x is going to be something like x by log x. Yeah? What happens is that this number of primes approaches x by log x from below up to a certain number, which is saying basically says asymptotic from below, and then it switches from something that goes from above. Yeah? So it starts approximating it from above at a certain number, switches at some place, and then goes on for some time, switches again, etc. The first number at which it switches is called the skews number, and it is 10 power 10 power 10 power 32. Okay? So it has genuine mathematical significance. Anyway, so now let's get back to, yeah. No, we will not talk about number theory. We will have to finish this geometry bit. Then we'll come back to number theory afterwards. Yeah. Okay. So now let's try to. So here, by piece of paper, I think what he meant was something that is flat, which means take a point on the piece of paper. Around it, it is flat. Now, why do you say that?
Because then there's no vertex at all.
Then there is no vertex at all. I can put a point and say this is a vertex. I want to say that every point is a curvature at if a point on the plane is chosen to be a vertex, so the intuition is perfectly correct. Yeah? But we would like to make that formal. Yeah? So why is the curvature at a point in a flat plane not curved at all? What measures that curvature? Before I give the answer, this is how we start thinking in mathematics. We want to finally assign something very precise. Yeah? And we want to get away from our fudgy way of thinking to something more precise. Yeah? So how are you going to nail it down? The curvature at a point in a flat plane is 0, but there is something where these things it's more. Yeah? And it should be the maximum for a tip of a tetrahedron, and least for an icosahedron, as he pointed out. So what's the number? How are we going to manufacture that number? Very good. So what is the sum of, so very good. This is excellent. So sum of the angles around that vertex, this would be a very good measure, but what would it be in the plane? It would be 360 degrees, correct? And that we want to say it has no curvature at all. So what we do is you look at the sum of the angles, look at the defect from 2 pi, and that defect is what we call curvature concentrated at that point. Okay? So that's it. So the surfaces of all these solids is homeomorphic to the sphere. Curvatures at vertices are different. How to measure curvature at a vertex V, and here's the formula. Once you have this, now you have a number. Yeah? 2 times pi is 360, pi is 180 degrees. So 360 degrees minus the sum of the angles of the faces. Each face is now a plane face, right? So there's a way of measuring angles. Yes?
So we're trying to taking each edge. So if I take the example of a dodecahedron, what we do is we take a pentagon and then
look at we'll do that calculation. You'll see exactly how it goes. Yeah? So this is the formula. So what does it mean? We are going to illustrate that right now with exactly the dodecahedron. So let's look at this dodecahedron. Yeah? So you look at this point and you want to calculate the total curvature, total angle around this vertex, which means the angle here in the Euclidean sense, angle here in the Euclidean sense, angle here in the Euclidean sense. Sum those three, subtract from 2 pi. That's the amount of curvature concentrated at this vertex. Yeah? Yes? Yes, somebody had something to say? 360? 2 pi minus this somewhere, yeah, so 360 degrees minus this. So what is, finally it boils down to calculation of this angle here, right? Then we are going to multiply that by 3 and subtract that number from 2 pi, yeah? That's going to be the curvature at that vertex, yeah? So what is the internal angle of a pentagon? Okay, so go back to Euclidean geometry, the sum of the external angles is 2 pi, yeah? Correct? 360 degrees. So how many sides are there? 2 pi by 5. And so if you look at this angle here, it's the external angle is 2 pi by 5. Inside will be pi minus 2 pi by 5. Yeah, that's 3 pi by 5. Yeah? 108 degrees. Correct? So that's the first thing. So theta I, which is the angle around a vertex on one side, is 3 pi by 5. That's the computation. How many faces are there at that vertex? 3. So total angle defect at a vertex is 2 pi. So 3 into 3 pi by 5 is 9 pi by 5. Subtract that from 2 pi. The amount of curvature concentrated at that vertex is pi by 5. This determines the sharpness of a point. Yeah? We'll do that rapid computation for some other things a little later. But this is the number. If the closer this number is to 0, the less sharp it is. The more it is, the larger it is, the more sharp it is. Okay? The more curved it is. Okay? But we want to do one more thing. Let's go back to how many vertices does the dodecahedron have? We want to compute total angle defect. Meaning what? You look at all these vertices. Each vertex now has angle defect pi by 5. Correct? 2 pi minus 9 pi by 5. How many vertices are there for the dodecahedron? And there's an easy way to count. 1, 2, 3, 4, 5. This is the front face. From here, one vertex each going out. The tips of those, that's another set of 5 vertices. Then they come together. Yeah? Meet at a vertex. Oh, hang on. That's right. Meet at a vertex. And then, so that's at this level. So this is the first level. There are 5. At the next level, this is 1, 2, 3, 4, and 5 here. Yeah? And then the middle guys are at the next level. So that's 1, 2, 3, 4, 5. And finally, there's the face opposite. That's 1, 2, 3, 4, 5. Yeah? So this is one way of counting. You can actually take this and put this. So Platonic solids have this property that you can draw so the edges actually give you a planar graph. Yeah? So it's 5, 5, 5, 5. So 5 into 4, 20 vertices. Right? So what's the total angle defect? If you count the angle defects, the total amount of curvature at all the vertices, sum them together, it's? Yes. Scribble and yes? Go ahead. It's a...
We got 3 pi by 5 for one of them, right?
Did we get 3 pi by 5?
Pi by 5. Yeah, so that's 20 by 4 pi.
20 into pi by 5, that's 4 pi. Good. So, oh, hang on. I'm not supposed to show this fact. So total curvature is 20 times pi by 5, that's 4 pi. Yeah? Okay, good. Now let's do it for a cube. Yeah? And let's go back and have an illustration of a cube. Oh boy. Yeah. Okay. So now look at a cube. What's the angle in a face? That's pi by 2. Correct? Angle at a single vertex. How many faces come together at a vertex? 3. What's the total angle? 3 times pi by 2. Angle defect is 2 pi minus 3 times pi by 2. How much is that? Pi by 2. How many vertices are there? 8. Total angle defect? 8 times pi by 2, 4 pi. Good. Do it for the tetrahedron. So if you have a tetrahedron, each face is an equilateral triangle. Angles are pi by 3. How many faces around the vertex? 3. Total pi. Angle defect? No. Angle defect at a vertex. Pi. So this is the answer to your question. The angle defect 2 pi minus pi is pi here. Yeah? For the dodecahedron, that was pi by 5. For this gadget, the cube, it's pi by 2. So it starts with pi. So it's just for these three, it's pi, pi by 2, pi by 5. It's decreasing, right? So this is the reason this angle that starts to decrease towards 0. It's becoming smoother and smoother. Okay, so the angle defect at a particular vertex is pi. How many vertices does it have? How many vertices does the tetrahedron have? 4. What's the total angle defect? 4 pi. So the total amount of curvature concentrated at a vertex for the tetrahedron, for the cube, for the dodecahedron, it's all 4 times pi. Yeah? This is a general fact. Oops. What is going on? Yeah, this is fine. Fact. Take something that is topologically, so all these gadgets are topologically a spheres. Yeah? So basically you look at that, assume that it's made of something flexible, blow it up, you're going to get a nice round sphere. Yeah? So, and if instead of having a nice round sphere, you make it into a collection of cells, you're going to be able to do this computation, you're going to be able to compute all these angle defects. The total curvature invariably turns out to be 4 pi. Locally, something is sharper, something is more blunt, right? But if you look at the total amount, that is a topological invariant, right? So the total amount of geometry contained in a sphere, it just depends on the topology of the sphere, not on its local geometry. Yeah? So total angle defect is a topological invariant for a sphere. Not only is it true for spheres, and this is where I'll stop. Now you should ask, what about a sphere with n handles? Yeah? So that was all our, right? So now let's do a cellulation of maybe a torus, maybe a genus 2 surface, also called a surface of a pretzel, etc., etc. So you look at a cellulation of a sphere with n handles. Do the sum of the angle defects. Yeah? So that's the total amount of curvature contained there. It turns out to be 2 pi times 2 minus 2n, or minus 2 pi times 2n minus 2. So where n is the number of handles. For the sphere, n is 0. Remove that. It's minus 2 pi times minus 2. That's 4 pi. Yeah? So we get back the. So this is essentially an incarnation of what we call the Gauss-Bonnet theorem. This was proven in the 19th century. What it says is that for surfaces, the total amount of geometry as measured by curvature is a topological invariant. However way you are going to deform it, whatever be the local curvatures, you can change the sharpness at a point. It will always have to be at the cost of sharpness at some other point. I'll stop there. Yeah.
So if it was for a torus,
Yeah. For what will it be for a torus?
so what is n equal to for a torus?
You tell me. You should by now you should have figured out. Yes, what is it for a torus? Yes, what is it? How many? What is it for a torus? This is a torus. 1.
But
So
then for a sphere it was 0. Yeah.
for a sphere it was 0.
Yeah.
So for a torus, what will the total curvature be?
It will be 0.
Yeah, it will be 0. Oh boy, terrible. Yeah, so that's what happens. So what happens is that for a sphere it's positive, 4 pi. For a torus it's 0. And you have higher genus, well, number of handles 2 and more. It starts becoming negative.
Minus 4 pi.
It will become minus 4 pi minus, 2 pi times, so it's, that's 2 into 2. Yeah, that's right. 2 into 2 minus 2. Yeah, so that's Euler characteristic will become minus 2. Yeah, so minus 2 times, minus 2 times, that's right. So it will become minus 4 pi, minus 6 pi, minus 8 pi, and so on. Yeah, that's how it is going to happen. Okay, so that's it. Yeah.
Why this formula does not write as minus 4 pi of n minus 1?
Factorize 2.
Because this 2n minus 2 has a nice significance. 2 minus 2n is a nice topological object associated to this thing. It's got a name. It's called the Euler characteristic. It's 2 minus 2n, not minus 2 pi. So the right statement is 2 pi times minus 2n plus 2. And minus 2n plus 2 has got it's got a name. You can put it as 4 pi times n minus 1. It's not very significant. That's all. Yeah. But it's the same thing.
In the previous, is it working?
Yeah.
In the previous step, when you mentioned that for most of the figures that we were talking about, the total geometry is 4 pi. I'm not very clear about that.
Here.
Are we saying that the curvature was 4 pi for almost all these figures?
Almost all.
Or all these figures?
For yeah, that's the correct statement. For all
But-
these figures, that's 4 pi. So what I've done the computation for the dodecahedron, for the tetrahedron, and for the cube. Yeah,
But we did come to the conclusion that some of these are more pointed than the others. So
that's right. So what does pointed mean? Pointed means at this point. Yes. What is total curvature? We are summing all these guys. So at each point it's pi. Yes. So 2 pi minus pi, that's pi, multiplied by 4. What you're getting here is pi by 5 multiplied by 20. Number of vertices are increasing. So the angle, the sharpness at a point is decreasing. The number of vertices is increasing. But if you want to say what the total angle defect for the whole polyhedron is, you'll have to sum all these angle defects. What the theorem says is that the sum of the angle defects is an invariant. For all these guys, not only for all these guys, for something much more general, take anything which topologically looks like a sphere, do this cellulation, and you're going to get the same answer. So in effect, what it also means is that if you want to have sharp curvature at all points, the number of vertices has to be small. Because the product has to be equal to 4 pi. The sum of all these things has to be 4 pi. Yeah.
Will this work for dimensions higher than 3?
Of course it does. That's why I put in that formula. 2 pi times Euler characteristic. Do you know what Euler characteristic is?
I have a vague idea.
No, you can't have a vague idea of Euler characteristic. You either have an idea of Euler characteristic or you don't. So we are very doctrinaire and very dogmatic in mathematics. Either you know it or you don't. Yeah.
It has something to do with V minus E plus F.
That's right. So V minus E plus F is the two-dimensional formula. The point is the Euler characteristic is something that can be defined in arbitrary dimensions. Do you know what Euler characteristic is of an n-dimensional complex? No. So this formula V minus E plus F, yeah, that can be generalized to arbitrary dimensions. As I said, that mathematicians have this very disconcerting habit of forgetting, okay, there's a two-dimension, nothing very special about 2. For 2, put in n, yeah, and have a nice formula, yeah. And what happens is that in all even dimensions, you can relate. That was done much. So Gauss-Bonnet is 19th century. Yeah? The generalization to all even dimensions, 2n dimensions, It's a theorem by a mathematician I have actually seen, somebody called Chern, Chinese mathematician, Xing-Shen Chern. It's called the Chern-Gauss-Bonnet theorem. You have a generalization in all even dimensions, 2, 4, 6, 8. In odd dimensions, that number turns out to be 0. It's not relevant. So the Euler characteristic of all closed odd dimensional manifolds is 0. So it's not going to give, it's probably true at some level, but it's going to give you something trivial in odd dimensions. In even dimensions, it does give you something. It does give you something very different. So there is something associated to curvature which you can integrate or sum. Yeah, so the way this is usually stated is in terms of an integral where you're not summing over vertices, but the curvature is at every point. Sum becomes an integral. That's not important, yeah? But if you have you can have this kind of polyhedral description in higher dimensions also. Yeah? It's called the Chern-Gauss-Bonnet theorem. That was proven around 1950, thereabouts. He passed away at the age of 90 plus, and I have seen him lecturing on mathematics, making a fundamental contribution when he was 83. Yeah, very inspiring person. Yeah.
Do we have any more questions?
I've taken up all the time.
I think that brings us to the end of this amazing mathematical session with Mahan Maharaj. A good round of applause for him. Just before you guys leave, I have 2 updates to share with you all. On the 10th of December at Bhaudaji Lal Museum in Baikala, we have Nagesh Bhosle, actor and director. He's going to talk about what it is to be an actor and a director. On the 15th of December at Kitab Khana Fort, where we have Savandatta. She's a writer and a vlogger, and she's going to tell you about her journey of making song vlogs. So go check her out on YouTube. It's Savandatta, Sawan. And yeah, it's called The Metronome. So go check that out. And Nagesh Bose is there. And once again, thank you, Mahan Ji. And thank you all for being here. Keep on coming. Next time, please bring 5 more people. Compulsory. Yeah, but we'll try and accommodate. Yeah, Bhaudaji is a bigger place. Thank you.
Okay.